Okay, now we're recording. Let me share the screen. Okay, so hopefully everyone can see the screen. All right. Can everyone see the slides?
Yes.
Okay. Did I turn the video off? Yes, I did, I think. Okay. So let me know if at one point you don't see the slides anymore or something, because sometimes for some reason screen sharing stops. But okay, so today's lecture is going to be on taboo search. We talked already last time about local search and various local search improvements. Taboo search and simulated annealing, which we will go through next time, are two meta heuristics that are designed to enable escaping from local optima. So we said that in classical local search, we search the neighborhood and we keep going until of a certain solution using a certain neighborhood definition or move operators. Once we reach a local optimum, we stop. We can also use various variations that we talked about last time, such as iterated local variable neighborhood search and so on. In taboo search, this is another method that is used to escape from these locally optimal solutions. So actually the main idea is simple. We use something called a memory structure to force the search to explore new areas of the search space. So we memorize some solutions that have recently been visited, and they become taboo. Taboo means forbidden. So when we select the next solution, we can search again the neighborhood, but certain solutions that we've previously visited are forbidden. Generally speaking, taboo search is a deterministic algorithm, but it is possible to add certain probabilistic elements to it. One thing that is important is to keep in mind is that downhill or uphill, depending on whether it's a maximization or minimization problem, moves are made only once we're stuck in a local optimum. So until we're stuck, we get to a local optimum, we practically act like a local search. Once we're in a locally optimal solution, we can escape by accepting also non-improving neighbors, and we'll go through that. So we're going to go through the basics of taboo search. We'll go through a number of examples today and also talk about some elements that are used to actually improve the efficiency of taboo search algorithms. Just as a point, so taboo search has become quite popular over the past 30 years. So about 30 years ago, it was proposed. Since then, there have been hundreds of papers, scientific papers that have been published that have investigated various applications of taboo search to various combinatorial optimization problems. So it has definitely been used quite a bit. Okay, so as I said, we'll talk about various concepts, these different memory structures, and we'll go through some examples. This picture we've already seen many times already now. So again, this taboo search falls into this category of improvement meta heuristics. Again, meta heuristic is a generic template. So what we'll show today is a generic template for this type of algorithm, which then of course you can customize depending on the actual problem that you're solving. And there are many parameters that we can play around with here. Okay, so it's an iterative single solution based meta heuristic. So what that means again is that we have a solution and we through a number of iterations, we try to improve this solution. It was developed in the 1970s by a guy named Fred Glover. And as I said, since then it's become very popular and has been applied to various types of combinatorial optimization problems. So the main idea is we use knowledge of previous experiences to make better decisions, and we guide this local search. Okay, let's look at just the basic idea. So let's say we have an initial solution. We search the neighborhood. Again, we define a certain move operator, which specifies a neighborhood structure, and we reach some kind of a locally optimal solution. So local search will give us this first local optimum. Once we're in this locally optimal solution and we look at all the neighbors, there is no better neighbor solution. Now, what taboo search allows us to do is to say, okay, looking at this neighborhood structure, we're going to accept the best neighbor, even if it's worse than what we already have. However, we're not going to allow every neighbor. We're going to allow only those neighbors that are not forbidden. So any for example, solutions that we visited previously might be those which are forbidden. On the other hand, that could be an explicit specification of what's forbidden. On the other hand, we might say, okay, we're going to forbid certain attributes of the solution. And we'll see some examples of what I mean by that. For example, let's say I have a binary vector as my representation. I could say, okay, you're allowed to flip every single bit. The move operator is a 1-bit flip, but you're not allowed to flip the 3rd bit. That's taboo. That's forbidden. So in that case, I'm not explicitly saying that a certain solution is forbidden, but I'm saying that a certain move is forbidden or a certain attribute of the solution. Or for example, a traveling salesman problem, you have a permutation as your representation. We can say, okay, it's forbidden to swap cities A and B or D and E. So there are different ways that we can specify moves that are forbidden. And we'll show some examples today. Okay, so the idea is to avoid cycling. Okay, we have an initial solution. We find a locally optimal solution. And now let's say, okay, we allow for a non-improving solution. We move to our best neighbor. It's worse than what we already have, but okay, we move to that solution. We check its neighborhood. Now what's going to happen? So if we moved to this second solution over here, now we check the neighborhood of this next solution and we go to the best neighbor. What's going to happen?
We return back.
We're going to cycle back, right? So what we want to do is after leaving the local optimum, the next best neighboring solution is again the local optimum, which we want to avoid. That's why we add this to our taboo list. So we say, okay, previously visited solutions, or as I said, certain move operators are going to become taboo or forbidden. The idea is to keep the search moving forward. And in that case, to jump out of this locally optimal solution. Now, one point that I could just want to make here is that one option would be, of course, to maintain a very long list of all solutions we have visited so far and say they are all taboo. Computationally, that's too complex, so too expensive computationally to do that. What we're going to do is say for a certain number of iterations, either a certain solution or a certain move is going to be forbidden, but only for a certain number of iterations. Let's say for the next 50 iterations or for the next 10 iterations, we're going to forbid that move. Then after a certain number of iterations, we allow it again. That number of iterations is going to be something that's called our taboo tenure or taboo length. And I'll get to that in a moment. Okay, so if we were to just visualize this taboo search run, the search moves forward for a certain number of iterations. We have to have some kind of stopping criteria. For example, so unlike local search, where simply we end as when we reach a locally optimal solution, in this case, we have to specify either a certain number of iterations or a certain time, execution time, or for example, a certain number of, if after a certain number of iterations we have not seen any improvements, then we stop the algorithm. So we need some kind of a stopping criterion. But let's say this is our initial solution, and what we want to do is this, what we've seen over here. So we want to be able to visit these different valleys in the solution space. In this simple illustration, the final solution, if we had gone through this search that we just showed, would be this one. This would be the incumbent or the best solution that we found. However, it may not necessarily be optimal. In this case, the optimal solution would be over here to the left. However, the search did not find it. That's why we'll talk about also some more advanced mechanisms such as that are actually used to diversify the search, and that's always important. So every heuristic, and not just taboo search, but every heuristic, we need to make sure that we have some kind of, on the one hand, depth or intensification, on the other hand, breadth. So we want to be able to diversify. That's something we need to keep in mind, how to do that. Okay, before we get into some examples, let me just terminology-wise introduce these terms. So we can use either something called explicit memory or attributive memory. Explicit means we're going to record the complete solution. So we want to, let's say, if our solution representation is a binary vector, we're going to maintain a list of all of, let's say, certain maybe elite solutions or good solutions that we have already found, so explicitly specify these solutions. On the other hand, attributive memory, we could record part of a solution or an attribute that, for example, which changes in moving from one solution to another, such as swapping two cities, adding a certain element to a knapsack, flipping a certain bit, or so on. So in that case, we're not memorizing actual explicit solutions, but rather moves that we have conducted. Okay, just as an example, okay, this is a bit, so this on the top it says maximize f of x. F is a bit erased here. So this we have just a simple example of a function where we're trying to find a value of x that maximizes this function. We've seen this example before. Let's say that x is represented in binary form with 5 bits, and this is one solution. So this is a binary vector. If we were to specify our neighborhood as a 1-bit flip, what we see illustrated here, this is the neighborhood structure. It has 5 neighbors. This is the value or the evaluation function, which we are trying to maximize in this case. So if we were to look at our neighborhood structure, this circled solution over here is the best neighbor, and we will move to that neighbor. So what we want to do now is we want to memorize our previous solutions so that we don't visit it again. We want to put it in this, let's say, a taboo list or something we call it. It's called a recency memory. So we're going to memorize the explicit solution, which would be our previous solution 10011, so that we know that we're not allowed to return to it anymore. Now, when we take this solution over here, 10001, and we enumerate all of its neighbors, we're not going to allow this one over here. Okay. On the other hand, if we were to do the same thing but use an attributive memory, we can say that, okay, this solution that is circled over here, 10001, was achieved by flipping the 4th bit. So to get from this solution over here to this one, we flipped the 4th bit. And rather than, oops. Hello?
Okay, we've lost the image.
You lost the image. Okay, hold on. Do
Screen,
you
sorry.
see it now, or do you see it now, or no?
Nope.
Okay, hold on, because Okay, are we back?
No, it's fine. Yep.
Okay. All right. So we rather than memorizing now the explicit solution where we were previously, which is this one over here, rather than memorizing this, we're going to memorize this move that we flipped the 4th bit. So we'll see how examples of how we could write this into some memory structure. But and then we'll say, okay, now we're going to take this new solution, this one over here. We're going to find its neighbors, but we're not allowed to flip the 4th bit. Okay, so rather than explicitly saying we're not allowing this previous solution, we're not allowed to flip the 4th bit. Okay. So what is this taboo list? So this taboo list is something that we call, this is a memory structure. It's a short-term memory structure where we record a certain number of last visited attributes or last visited solutions, or rather attributes or moves. So these solutions, as I said, can be either moves that are forbidden, for example, for as long as they remain in the list. Oftentimes, this is some kind of a circular list, let's say a first in, first out type of list. So let's say if it's a size 3, it has 3 elements, then we can say that this taboo list is updated after cyclically after each iteration. So in the previous example, we would say that flipping the 4th bit would be taboo for 3 iterations, and then after that we would again allow this 4th bit to be changed. So the idea of this short-term memory in terms of a taboo list is to prevent cycling. So we want to prevent going back to some kind of solutions that we have already found. as I said, the most popular way is to represent the taboo list is to record these move attributes. And that's going to, of course, directly depend on the neighborhood structure that we use. Okay, this we've already said, so we're trying to avoid getting stuck in locally optimal solutions. Up until the point where we reach a local optimum, we proceed simply as a local search. But once we are in a locally optimal solution, at that point, we accept non-improving solutions, which are not in the taboo list. So we don't allow backtracking. So a certain number of previously visited solutions are taboo, which avoids, as I said, cycling between neighboring solutions. Just as an example, okay, let me go over here. Can you see this board?
Yes, we can see it.
Okay, let's say that we have a representation which is a permutation vector. So let's say we have A, B, C, D, and E. So this is a permutation vector. Let's say that our neighbor is exchanging two elements. So our neighborhood is swapping two elements. Okay, so given a solution, then a move is actually represented by two indices. So let's say our move, we said that we swap, let's say, indexes I and J. So if we have a certain solution, let's say a certain solution S, we get to a new solution S prime by swapping I and certain I and J. So let's say if we want to move from this solution to another solution, A, C, B, D, E, we reach this solution. So our move would be switching or swapping indices 2 and 3. So now the inverse move is stored in the taboo list and it is forbidden. What we could do is we could have, let's say our taboo list is a size 3. We could have a taboo list that looks like this, where we say, okay, it's forbidden to now swap, to swap indexes 2 and 3. Here we have nothing, it's empty. Then in the next iteration, let's say our next solution is, the best solution is achieved by swapping 1 and 5. What we're going to do is then update this taboo list, okay? Move, say, okay, now we're not allowed to swap 1 and 5. We move what we had previously 2 and 3 over by 1 spot. Okay, and now we're not allowed to swap 1 and 5. We're not allowed to swap 2 and 3. In this case, in this example, our length of our taboo list, or so-called taboo tenure, is equal to 3. Okay, so let's say then in the next iteration we swap 4 and 5. Okay, so then now we're not allowed to swap 4 and 5. 1 and 5 has moved over. 2 and 3 has moved over, and so on. In the next iteration, let's say we swap 2 and 3, then 2 and 3, 4 and 5, 1 and 5, but we are now allowed to swap 2 and 3. So 2 and 3 has dropped out of the taboo list. In this case, as I said, we have a first in, first out kind of a list, and we are maintaining in this memory structure the indexes which we are not allowed to swap. A stronger taboo would be, let's say, let's go back to this first case where we swapped 2 and 3, disallowing any move involving either 2 or 3 for a certain number of iterations. That would be, let's say, a stronger example of a taboo, where then we're not allowed to touch those. Okay, let's look at another example. Let's say if we have a traveling salesman problem, which is again the same type of representation. So again, let's say that we have A, B, C, D, E. Sorry, this keeps. Okay. So let's say that we have a traveling salesman problem, and these are the different cities that we need to visit. Another way of, let's say, illustrating this recency-based memory would be, we could draw it like this. So B, C, D, E, A, B, C, D. we could have something like this, saying, let's say, 0, 3, 1, 2. Okay, these are irrelevant. 0, 1, 0, 2, 1, 0. And what something like this could mean is that, for example, swapping cities C and A, what we have over here, is not allowed for the next 3 iterations. Swapping cities D and B is not allowed for the next 1 iteration, and so on. So we could use a memory structure like this, which is then updated after every iteration. Once this value is 0, so we can see, for example, from this this picture here, that we have never swapped cities E and D. So this is 0, and so on. So we can see what we're allowed to swap. Sorry, not that we've never swapped, but that we are allowed to swap cities E and D since that value is 0. After the next iteration, we decrease these values given in this table. And for example, if in the next iteration we were to swap E and D, then that value over here would become 3. The remaining values would be decreased by 1. So 3, 1, 1 over here would be decreased by 1. So this is just another way of, for example, illustrating or keeping this recency-based memory. Let's say that we have, let's say another example, that we have a vehicle routing problem so a classical vehicle routing problem where we have some kind of a depot, okay, a depot over here. And we have a certain number of customers. Let's say customers V1, V2, V3, V4, V5, V6. Available at this depot, we have, let's say, M identical vehicles. Each vehicle has a certain capacity Q. We need to find routes which start and end at the depot. Each customer has to be visited exactly once. Each customer, so each vertex VI has an associated demand. So QI is the demand of customer VI, and service time. So let's say TI, once the vehicle arrives at a certain customer service time of customer VI. So once the vehicle arrives at customer, let's say V2, it's going to spend T2 amount of time there. So for example, to unload certain resources that it has bought or so on. Each arc, so each arc VI, has a certain cost and also a certain travel time Tij. Okay, so what we're trying to do is minimize so the demand of each customer cannot, the demand of all the customers on one route cannot exceed this overall capacity of one vehicle that is going along that route. The total duration time of each route does not exceed a certain, also, let's say, amount of time which is given, and the total cost of routes we're trying to minimize. So one example could be that we go from, so we have one route, this is one route, and let's say that we have another route that goes like this, which is route 2. Okay, an example move operator could be moving, let's say, V3, so customer V3, from route 1 to route 2. In that case, so if we have, again, our depot, V1, V2, V3, V4, V5, and V6, then we simply add V3 to route 2, okay? This is route 1 and this is route 2. In this case, moving V3 back from route 2 to route 1 could be a move which we forbid for a chosen number of iterations. So we could record this triplet, let's say V3, R2, R1, and say, okay, for a certain number of iterations, we're going to say that this move is forbidden. A stronger taboo, or a stronger, let's say, constraint would be that saying, okay, we're not allowed to move customer V3 going from R2 anywhere else. So we're not allowed moving, we're prohibiting it, or sorry, just 1 second. A stronger taboo move would be saying that we want to prohibit moving V3 back to R1, no matter where it is. So if it's, so we just record, let's say V3 and R1 and say we're, no matter if, even if we've moved customer V3 somewhere else, we cannot move it back to R1. An even stronger taboo move would be saying, okay, we're not allowed now for the next number of iterations to touch customer V3. So it has to stay, that customer has to stay in the route where it is currently. So it can't be moved at all for a certain number of iterations. So these are examples of different moves which we can, let's say, add to our taboo list and forbid for a certain number of iterations. Okay, let me go back to the slides. So again, this taboo list is maintaining these move attributes, which we are saying are now forbidden. The structure depends on whether we're using explicit or attributive memory, and I sort of showed you some examples. So let's say we want to keep track of certain indexes which we are not allowed to flip in an assignment problem, or certain, let's say, cities or edges which we cannot exchange in a traveling salesman problem, or certain customers which we are not allowed to move from one route to another in a vehicle routing problem, or certain bits which we're not allowed to flip in a, let's say, satisfiability problem, or so on. An important design issue is this taboo tenure. So for how many iterations are the solutions in the list going to remain forbidden? If it's too big, so if we say that for very many iterations, let's say, we are not going to allow a certain move or a certain solution, what might happen is that the search might become too restrictive. What might happen is also that certain solutions, we're going to ban certain solutions which might actually be provide a good solution quality, but we are banning them for too long. So the problem is that we might need to decrease this length of time that we're going to forbid a certain solution. On the other hand, if it's too small, so if the length of this taboo list is too small, the number of iterations is too short, the search might return back to a locally optimal solution. So we might end up cycling back to already seen solutions. This compromise between too big and too large is something that will ultimately depend on the landscape structure of the problem and on the associated instances which you're using. So this is something that needs to definitely be played around with and tuned when designing an efficient taboo search algorithm. The size of the taboo list, what I just wanted to also point out here, is that it can be static. So we say that, okay, the size is simply a static value, which somehow depends on, let's say, the size of the neighborhood or the instance size and so on. It could be dynamic, so something that can change during the course of the search. Or, for example, we may adapt the size of the taboo list if we see that we are starting to cycle. So if we see that we're starting to return back to already seen solutions, maybe we can increase the size of the taboo tenure and so on. So a good option is to dynamically adapt this size of the taboo list during the course of the search. Okay, let me go through another just quick example before going to some, let's say, more advanced ways of how to diversify the search and how to intensify on one hand and then diversify on the other hand. Let's again use this very simple example. This isn't necessarily the best example or representation, but it's illustrative. So again, we have the same example. We have x as an integer encoded in a binary form with 5 bits. And we have an initial solution which has a value of 2,349. Okay, so we define our neighborhood as a 1 flip, and let's say we're going to terminate after 6 iterations. Okay, We're only going to use this short-term attributive memory, so we're not going to use any diversification at this point. We're going to say that our taboo list is going to record the position of the last changed bit, and we're going to ban that change for the next 3 iterations. So that means that our taboo tenure, or the length of our taboo list, is going to be 3. Okay, so we have a vector of 5 integers with values in 0, 1, 2, 3, or 4, 0, 1, 2, 3. And each is going to correspond to 1 bit in the solution representation and indicate how many iterations is going to change, for how many iterations changing that bit is going to be a taboo. So this is going to be our taboo list, which is shown on this slide. Initially, all values are set to 0. And we'll see how that's going to now be adapted over the course of the search. Okay, so we start with our current solution S. We have our incumbent solution. That's our best solution so far, which is the same one. We have our taboo list, which is currently empty. And we have this neighborhood 1 flip. So we've found all the neighbors by flipping this, by flipping 1 bit. Okay, what now? So we're trying to maximize our function. We find the best neighbor. In this case, it's better than the incumbent solution that we have. Okay. So our best neighbor is this one. It was achieved by flipping which bit? So we obtained it by from the current solution. We changed the 4th bit. So how are we going to now update our taboo list? We indicate that now flipping the 4th bit is going to be taboo or forbidden for the next 3 iterations. So we write that like we have here. So our taboo list is going to be 0, 0, 0, 3, 0, meaning that for the next 3 iterations, flipping the 4th bit is going to be forbidden. Okay, we check whether this solution is better than the one we already have. Yes, it is. So we update the incumbent solution. Now this is our best. This is going to now be our best solution that we have so far, and we maintain that solution as the incumbent. Okay, so we go after the first iteration, we have our current solution, we have the taboo list, and we have the incumbent solution, which is also in this case equivalent to the current solution. Okay, we take our solution, we generate our neighborhood. What we see now is that flipping the 4th bit is taboo, so we're not going to do that. We're not allowed to do that, so we can flip the 1st, 2nd, 3rd, and 5th bit. And these are our neighbors. We find the best neighbor, which is not taboo. And we say, okay, that's this one. It becomes the new current solution. Okay. It was obtained by flipping the 5th bit. So now we're going to update our taboo list. Now, going back to our 4th bit, since 1 iteration has already passed, now we're going to decrease this number. It was 3 before, now it's 2. Now we can say, okay, 4th bit, now for 2 more iterations, we're not allowed to flip it, but now we flip the 5th bit. That one is now forbidden or taboo for the next 3 iterations. Okay, you guys are following me? Just jump in if there are any questions. Okay, so we're just decreasing now these counters. Okay, we check whether the solution is better than the one we already have. Yes, it is. So we're going to update our incumbent solution, and that's going to be now our new best solution. Okay, let's keep going. So after the 2nd iteration, we have our current solution, we have our updated taboo list, and we have our best solution so far. Okay, now we generate its neighborhood. Now what we see is actually that now we have 2 taboo solutions. Flipping the 4th and 5th bit is forbidden. So we're only allowed to flip the 1st, 2nd, and 3rd bits. And now what's going to happen? So now our best neighbor, we pick the best neighbor. In this case, it's not going to be better than what we already have, but it's going to be the best out of the neighbors which are not taboo. Okay, we have our best neighbor. It was obtained by flipping the 3rd bit. So now we're going to set this counter to 3, decrease this one from 2 to 1, and decrease this one from 3 to 2. Okay, so we keep going. Is it better? Is this solution better than the best solution we already have? No, it's not. So we're not going to update the incumbent solution. Our current solution is now 1, 0, 1, 0, 0. We have our old incumbent solution from our previous iteration, and we have our updated taboo list. Okay, now we keep going. So now it's taboo to flip the third, fourth, and fifth bits according to our taboo list. We pick the best neighbor. Okay, we keep going. So we're just repeating ourselves. So this neighbor was obtained by flipping the first bit. So now we see that, okay, now for the next 3 iterations, we're not allowed to flip the first bit. We have never so far flipped to the second bit. We haven't flipped it yet. These counters are reduced, and what we see that now this counter for the fourth bit has been reduced to 0. So from now on, we're allowed to, again, flip the fourth bit. Okay, is it better than what we already have? No, it's not. So we're not going to update the incumbent solution. Okay, so now we have our taboo list. So again, this taboo list is simply a recency memory. So we're only remembering the last or maintaining this, let's say, recent these recent moves. We're not going to, we're not maintaining in this memory structure, let's say, a long-term memory, which we'll see can be introduced as an additional memory structure to diversify the search. But we'll get to that in a moment. Okay. So we have the current solution. Now it's taboo to flip the first, third, and fifth bits. We look at the second and third solutions. The best neighbor becomes the new current solution. We keep going. Okay, so now we update again the taboo list. Now we flip the second bit. These counters, this is decreased. This one is set to 3. Okay, and after iteration 5, I'm going to just quickly click through this, since we're this is all the same logic. So after iteration 6, which is obtained by flipping the fifth bit, we check whether the solution is better. No, it's not. And after iteration 6, we have found this is our incumbent or best solution. Our taboo list is shown here, and our current solution. We said the stopping criteria was going to be 6 iterations, so this is the best solution we have found so far, which again is not the globally optimal solution in this case. An alternative structure for the same taboo list could be also some kind of a first in, first out buffer of size 3, simply saying that, okay, after indicating which bit we're not allowed to flip. So we could say, okay, after the first iteration, we're not allowed to flip bit 4, then after the second iteration, flip bit 5, then bit 3, and so on. So this could be an alternative structure. Okay, I wanted to go now through one more example, but maybe this is a good time actually to take a short break, and then we'll go back to more examples. Okay. Let me go back to